Oh, yeah. Okay. Do you hear me? Okay.
Yeah. We hear you well.
Thank you. Thank you for the introduction. And in this talk, we will consider mathematical models that evolve according to stochastic dynamics in order to describe some properties of real-life systems in the framework of non-equilibrium statistical mechanics. And in particular, we will focus on the metastable behavior of a b-dimensional lattice gas with strong anisotropic interactions that evolves under Kawasaki Dynamics. And this is a joint work with Francesca Romananari. I will start by introducing the metastability phenomenon, both from a physical and from a mathematical point of view. And then I will define the model that we analyze. And for this model, I will give you the three main results that we have derived. And then I will give you an idea of the dynamics from an heuristic point of view. And finally, I conclude with some open problems that are related to this work. So metastability is a dynamical phenomenon that occurs when a thermodynamic system is close to a first-order phase transition. We have a physical system that is described by some parameters. And referring to this picture, suppose that we fix our parameters at a point P here, then we have that our system is in equilibrium in a phase A. While if we fix our parameters at a point P prime, then we have that our system is in equilibrium in a phase B. With this black line here, I represent the coexistence line between phase A and phase B. And what we do is to fix our parameters at a point P double prime that is very close to the coexistence line, but not on it. So we have that the phase A corresponds to the metastable phase and the phase B corresponds to the stable phase. So we suppose that our system starts at time zero in the metastable state A, and it evolves according to a chosen stochastic dynamics to the stable state B. We observe that the system is trapped here in the metastable phase for extremely long time until it undergoes a sudden transition at some random time to the stable state. In this picture, I report the Hamiltonian energy H, and we observe that a metastable state corresponds to a local minimum of this Hamiltonian energy, while a stable state corresponds to a global minimum of the energy. So our goal is to characterize for a system that is described by a Markov process, the transition from a local minimum to a global minimum of the energy. And during this talk, we will focus only on the case in which there is a unique metastable state and a unique stable state. So for our model, the energy landscape has the shape that is represented here, a unique metastable state, so a unique local minimum of the Hamiltonian, and a unique stable state, so a unique global minimum of the energy. When we study metastability, there are three main questions that are addressed. The first one is the study of the typical transition time from the metastable to the stable state. The second one is the geometrical characterization of some particular configurations that are known as critical droplets. And roughly speaking, they are here along this saddle. And roughly speaking, these configurations will be crossed with probability tending to 1 in some limit that I will explain later on. The last questions concern the description of the tube of typical trajectories that are followed by the path during the transition from the metastable to the stable state. In nature, there are many examples of metastability, like superheated or supercooled water. In these two figures, I represent the hard rime and soft rime phenomena that occur when the droplets in the air are liquid, but their temperature is under 0 degrees. And what happens is that these droplets immediately freeze when they hit some obstacle. So here we can see that there is this creation of ice needles on these trees. There are other examples of metastability like supersaturated gas or ferromagnet in opposite magnetic field. So now we can define our model. We consider a box lambda that is finite inside the b-dimensional square lattice, and we assume that this box is sufficiently large. With each site x in this box lambda, we associate an occupation variable eta of x that can be equal to 0 or equal to 1. Eta of x is equal to 0 if at site x there is no particles, but eta of x is equal to 1 if at site x there is one particle. So we allow the presence of at most one particle per site. We denote by eta a lattice gas configuration that is eta of x with x in lambda and belongs to our configuration space key that is 0, 1 up to lambda. And we define interactions between particles by defining the Hamiltonian energy H that I report here in this formula. This first sum takes into account all the unoriented horizontal bonds between nearest neighbor particles. Indeed, this term eta of x times eta of y is different from 0 if and only if both the terms eta of x and eta of y are equal to 1. That means that at site x there is one particle and at site y there is one particle. This term here, minus u1, is a constant that is strictly negative and represents the binding energy associated to an horizontal bond. The second sum here is the corresponding term for the vertical unoriented bonds. And this term minus u2 is again a negative constant that now represents the binding energy associated to a vertical bond. The last sum counts the particle in lambda, and this factor here, delta, is a constant greater than 0 that is known as activity parameter. So to summarize, each horizontal bond contributes to the energy by a factor minus u1, while each vertical bond contributes to the energy by a factor minus u2, and each particle contributes to the energy by a factor delta. Without loss of generality, we assume that u1 is greater or equal than u2. But why we distinguish horizontal and vertical bonds? If u1 is equal to u2, then we are in the so-called isotropic case. Indeed, we have no distinction between horizontal and vertical bonds. But now we suppose that we are in the so-called anisotropic case. So for the moment, assume that u1 is greater than u2, and in particular, u1 is different from u2. And thus, we need to distinguish between horizontal and vertical bonds because they contribute to the energy by a different factor. Then I will explain in more detail the regime of parameters that we take into account. So now we want to define the dynamics inside our box lambda, that is Kawasaki Dynamics. So consider two different configurations, eta and eta prime, and we say that eta and eta prime are connected via Kawasaki Dynamics if there exists a bond such that eta prime can be obtained by eta via one of the following steps. So referring to this picture, if we are in the situation here depicted in red, so the bond B goes from the site X to the site Y, and it belongs to the interior of lambda, then the dynamics exchanges the position of X and Y. So for example, in this situation, we have that eta of X is equal to 1 because at site X there is one particle, and eta of Y is equal to 0 because at site Y there is no particle. So the dynamics moves the particle from the site X to the site Y. So we have that eta prime of X is equal to 0 and eta prime of Y is equal to 1. If we are in the situation depicted in violet, so now the bond from the site X to the site Y exits from the boundary of lambda, we have that the dynamics decreases the number of particles because inside the lambda, because now the particle goes from the site X to the site Y. While if we are here in the situation depicted in green, So the bond enters the boundary of lambda. We have that the dynamics increases the number of particles inside lambda because now the particle goes from X to Y. So we can conclude that Kawasaki Dynamics is conservative inside the interior of lambda, because conservative in the sense that the number of particles is conserved, because in the interior of lambda we have simply the movement of particles. But we are defining a dynamics with open boundary conditions because we allow the annihilation and the creation of particles at the boundary of the box. And this mimics the effect of an infinite gas that is outside our box lambda. So we define Kawasaki Dynamics with open boundary conditions as a discrete time Markov chain with transition probabilities given by the Metropolis algorithm. In particular, we define the transition probability from eta to eta prime equal to 0 if these two configurations are not connected via Kawasaki Dynamics. Otherwise, this transition probability is equal to a constant times an exponential function that depends on the energy difference of these two configurations and on beta, where beta is the inverse temperature, and we are interested in the limit as beta goes to infinity. That corresponds to the limit as the temperature goes to 0. In particular, if the energy of eta prime is greater than the energy of eta, we have that this positive part here is greater than 0, and therefore the transition probability is exponentially small in beta. Otherwise, if the energy of eta prime is less than the energy of eta, this positive part is equal to 0, and thus this transition probability is a constant. We define then the transition probability from eta to eta as 1 minus the sum overall the configuration eta prime different from eta of the transition probability from eta to eta prime. We can define a particular measure associated to the Hamiltonian, the Gibbs measure mu, that is defined as 1 over the partition function z times the exponential of minus beta times the energy of the configuration. And we observe that the dynamics is reversible with respect to the measure mu, and therefore we conclude that the Gibbs measure is a stationary distribution for Kawasaki Dynamics. So we have defined our model and our dynamics, and now let us see the regime of parameters that we consider. So we consider a fixed volume lambda, arbitrarily large, and the asymptotic regime at low temperature that corresponds to beta goes to infinity. Now we fix the parameters U1, U2, and delta such that delta belongs to the interval from U1 to U1 plus U2 that corresponds to the metastable regime, and such that U2 over U1 plus U2 minus delta is not integer. This second assumption is basically a non-degenerate assumption, and I will explain it in more details later on. There are three interesting cases. The first one occurs when U1 is equal to U2, and this regime is known as isotropic case. The second one occurs when U1 is greater than 2 times U2, that is known as strongly anisotropic case. And the last one occurs when U1 is greater than U2, but less than 2 times U2, and this is known as weakly anisotropic case. During this talk, we will focus only on the strongly anisotropic case, so we assume that U1 is greater than 2 times U2. For this model, we have proven that the box full of particles, the state 1, is the unique stable state, and the empty box, the configuration with all zeros, is the unique metastable state. So the metastability problem for our model consists in starting from the empty box here, that is the metastable state, and study the transition to the full box, that is the stable state. Before entering in the details of the results, I want to give you an overview of results that are already present in the literature for Kawasaki Dynamics. So the study of this model was initiated in 2000 by the Norlander, Olivieri, and Scoppola for the two-dimensional isotropic lattice gas. And in particular, they investigated the transition time, the critical droplets, and they gave some results about the tube of typical trajectories. In 2005, Godiguier, Olivieri, and Scoppola fully identified the tube of typical paths. And 2006, Bouvier, Norlander, and Nardi sharpened the previous results for the transition time and critical droplets. In 2005, Nardi, Olivieri, and Scoppola analyzed the weakly anisotropic case, giving results for the transition time, critical droplets, and partial results for the third question of metastability. And last year, we have derived similar results for the strongly anisotropic case. In 2012, the Norlander, Nardi, and Troiani consider a slightly different version of this model that is known as two types of particles model, that basically means that are particles of type 1 and of type 2 with different interactions between each other. And they analyzed the first and second issues of metastability. Last year, we have also described the critical droplets with more detail for all these three cases. Concerning the three-dimensional lattice, the Norlander, Nardi, Olivieri, and Scoppola in 2003 analyzed the transition time, the critical droplets for the isotropic case, giving also some results about the tube of typical trajectories. But actually, there are no known results for the three-dimensional anisotropic lattice gas. So one of the goals of this talk is to describe the critical droplets from a geometrical point of view. So now I want to introduce a geometrical representation of the configuration as a subset of the real plane. So first of all, I introduce free particles as particles that don't interact with any other particles. And a configuration eta without the free particles is known as clusterized part of the configuration, or simply cluster. So we can define the set C of eta cluster as the union of 1 times 1 closed squares centered in the occupied sites of the cluster. In order to visualize these definitions, I report here an example of a configuration. So the black dots represent the particles that are in lambda. So here there is a particle, here there is a particle, here there is a particle, but also here, here, and so on. And then we draw a 1 times 1 closed squares centered in this site. So here we draw a 1 times 1 closed squares. Also here we draw a 1 times 1 closed squares, and so on. And then we take the Euclidean boundary of this set that is represented by these black lines. We observe that the three particles on the right-hand side are free because they do not interact with any other particles of the configuration, while the other part is the cluster. And with this dotted line, I represent the circumscribed rectangle of the configuration that is the smallest rectangle that contains the cluster. So before giving the precise theorems that we have derived, I need to introduce a specific set P that is composed by the union of a set P1 and the set P2. I don't want to enter in the details of this set, but here in this picture, I report on the left-hand side an example of a configuration in P1, and on the right-hand side, an example of a configuration in P2. This vertical length L2 star is defined here as the upper integer part of U2 over U1 plus U2 minus delta. Before, I've mentioned that we require that this ratio is not integer because in our computations, we need to write L2 star as this ratio plus a quantity that is strictly greater than 0, but also strictly less than 1. So we require that this ratio is not integer. We note that the configurations in P2 have one free particle, while configurations in P1 have no free particles, and both configurations have horizontal length that is approximately twice of the vertical length. It is possible to prove that configurations in P have the same energy that we set equal to gamma, and here I report the explicit expression of this constant that depends on the parameters U1, L2 star, U2, and on the parameter epsilon that we define as U1 plus U2 minus delta. And we assume that epsilon is much less than U2 in order to have the critical length L2 star much greater than 1. And for instance, it is enough to assume that epsilon is less than U2 over 100. So now we are ready to give you the first theorem that answers the first question of metastability, in which we prove a convergence in probability, expectation, and law of the transition time. If the size of the box is sufficiently large, for any delta greater than 0, we have proven that the probability that starting from 0, the first heating time in 1, that is the stable state, that is bounded from below by the exponential of beta times gamma minus delta, and bounded from above by the exponential of beta times gamma plus delta, tends to 1 in the limit as beta goes to infinity. And I recall that gamma is the energy of the set P, and we have the explicit expression of gamma. So we have proven that the nucleation time from 0 to 1 behaves in probability as the exponential of beta times gamma in the limit as beta goes to infinity. Moreover, we have proven that the expected value of this transition time behaves as beta goes to infinity as the exponential of beta times gamma. And if we define a suitable rescaling factor T beta, we have proven that asymptotically in beta, the transition time after this suitable rescaling has an exponential distribution with this factor T beta that behaves as the expected value of the transition time as beta goes to infinity. So now I want to give you the second theorem that regards the critical droplets, and in particular, we prove that the set P is a gate for the transition. And roughly speaking, this means that all the paths that connect the metastable to the stable state cross this set with probability 1. We observe that the dynamics remains trapped inside the metastable state. So we define the time theta 01 as the last time in which the dynamics is in 0 before reaching 1. And then we define the time theta 0 P1 as the first time after theta 01 in which the dynamics is in P. So we are focusing on the last excursion from the metastable to the stable state. And we have proven that the probability starting from 0, that this time theta 0 P1 is less than the first heating time in 1, tends to 1 in the limit as beta goes to infinity. So we have proven that all the paths that connect 0 to 1 cross this set P with probability tending to 1 in the limit as beta goes to infinity. Now I present the last theorem that gives partial information, only partial information about the tube of typical paths. So consider that eta is a rectangular configuration that is contained in a rectangle with horizontal dimension equal to 2L2 star minus 3 and vertical dimension equal to L2 star minus 1. Then we have proven that the probability that starting from this configuration eta, that the dynamics reaches 0 before reaching 1, tends to 1 in the limit as beta goes to infinity. So these rectangles are subcritical in the sense that starting from them, the dynamics tend to shrink to the empty box before reaching the full box. while if eta is a rectangle that contains a rectangle with horizontal dimension equal to 2L2 star minus 2 and vertical dimension equal to L2 star, we have proven that the probability that starting from eta, the dynamics reaches 1 before reaching 0 tends to 1 in the limit as beta goes to infinity. So these rectangles are supercritical in the sense that starting from them, the dynamics tends to grow to the full box before shrinking to the empty box. And moreover, this means that the horizontal critical length is 2L2 star minus 2, and the vertical critical length is equal to L2 star. So now I want to give you an idea of the dynamics from an heuristic point of view. To this end, I need to introduce the energy barriers from a configuration eta to another configuration eta prime along a path omega that connects eta to eta prime as the difference between the maximal 8 in energy reached along this path and the energy of the starting configuration. Suppose now that eta and eta prime are two rectangles, so all the possible transitions from eta to eta prime are the following. Adding or a row or a column. If we add a row, then we have that for the starting rectangle, the vertical length increases by 1, while the horizontal dimension remains constant, while we have the opposite situation if we add a column. And namely, we have that the horizontal length increases by 1 and the vertical length remains constant. While we are in the opposite situation if we remove a row or if we remove a column. There are two other types of transitions, that is moving a row into a column. That means that now the horizontal length increases by 1 and simultaneously the vertical length decreases by 1, or moving a column into a row, that means the opposite move. So here in this slide, I report all the energy barriers for these transitions, but I want to focus only on the transition add column. So here I report an example of transition of this type. So here we have our rectangular configuration eta, and here we have our target configuration eta prime that has a column added here. So in order to add a column, first we need to add a free particle inside the box lambda. So the energy increases by a factor delta. And then we have to attach here the free particles in order to add a column. So there is a creation of an horizontal bond that contributes to the energy by a factor minus U1. So the energy increases by this factor. Then we proceed similarly. So we add another free particle, and so the Hamiltonian energy increases by a factor delta. But now when we attach this free particle here, we have the creation both of an horizontal and a vertical bond. So now the energy decreases by a factor U1 plus U2. So when we proceed in this way, when we create another free particle, now the energy increases by a factor delta, but delta is less than U1 plus U2. So this configuration here has energy less than this fourth configuration here. So in order to compute the energy barrier for this transition, we need to consider the difference between the energy of this fourth configuration and the first one. That is 2 delta minus U1. So this is the energy barrier for this transition. Okay, in this picture, I resume the dynamics heuristics for our model in the strongly anisotropic case. So I recall that strong anisotropy means that U1 is strictly greater than 2 times U2. So each point in this picture represents a rectangular configuration and the horizontal length of this rectangle is reported here on the x-axis, while the vertical dimension is reported here on the y-axis. These arrows among all the transitions that connect two rectangular configurations are the ones with the smallest energy barriers. So for example, in this region here, these arrows that goes from the left to the right means that here, the smallest energy barrier is obtained for a transition of the type add column, while here is obtained for transition of the type remove column, and here is obtained for the transition move row into a column, because here we have an increasing by one of the horizontal length and decreasing by one of the vertical length. We note that there are three regions that are attractive for the dynamics and are T1 prime, T2 prime, and T3 prime. And we have proven that the critical droplets, namely the configurations in the set P, appear in the region between T1 prime and T2 prime, namely in correspondence of a vertical length equal precisely to L2 star. And we have seen before that configurations in P have horizontal length that is approximately 2 times the vertical length, and namely here, this value is approximately 2 times L2 star. So this is the dynamics heuristics for our model in this regime. So to conclude, I present some open problems that are related to this work. So in this talk, we have focused on the two-dimensional model with open boundary conditions. So a much harder problem is to consider a two-dimensional model with periodic boundary conditions. So the annihilation and creation of particles at the boundary of the box is not allowed anymore, but we fix a sufficiently large number of particles inside our box, and then we study the dynamics into a smaller box inside. Another possible issue to be addressed is the geometrical description of the tube of typical trajectories for the two-dimensional anisotropic model, both for weak and strong anisotropy. In such a way, the third question of metastability is fully addressed. And finally, we can imagine to study the transition time and the gate for the three-dimensional anisotropic model. For example, at the beginning, one could consider only two different binding energies, U1, U1, and U2 in the three directions, and then extend this study also by considering in the three directions, three different binding energies, U1, U2, and the U3. And with this, I conclude, and I thank you for the attention.
Thank you very much, Simone. It was a very nice talk. I really like the pictures. And okay, so let me first stop the recording.